Okay, I think we are streaming. Give it a couple seconds here to soak. Hey, we are streaming. I'll be dang it, I'm always impressed when this works. Hello, everybody. How are you? We have multiple people here today. We started out, we didn't think Ben would be able to join us till halfway through, and Mike stepped in, but Ben is here. So we're going to go ahead and talk about an exciting topic with all three of us. So, hi, Ben. How you doing?
It's good to see you both. Thank you.
Yep. Hi, Mike. How are you doing?
Howdy. Yeah.
Thanks for joining us.
My bandwidth is very limited too, so it's probably good to have one other more interesting person who also has a good internet.
Just in case.
Yeah. So we just had a panic. That's why we're 2 minutes late. Not a panic, but the software threw it's, I don't have permissions to talk to Google type thing or YouTube. But we worked through them and everything. Hey, before I get going too long, I want to thank Bill Peloton for, I want to make sure I'm pronouncing his last name right. He sent me my own TED, and he signed it for me, which is very cool because I signed his. So thank you, Bill, for the TED. So now I have one I can wave around. So thank you for that. So how's your week been, Ben? What's new in your world?
Well, we haven't spoken much other than a bit of chat on Discord since before Thanksgiving holiday here in the US, right?
Right.
So it's been. I had a holiday week off. I thought I would get a whole lot of work done on my office and projects and this and that because I took the week off. I got a little bit more done, but hardly enough because there were a lot of other family activities going on too. So, but that was good. It was good to have that. And
was this your first Thanksgiving in America? Have you been here for a while? And
I've been here for a while,
Yeah.
and I first moved to the United States actually at the beginning of November in 2005. So I had my first Thanksgiving very soon after coming to the US, and was invited to a friend's house, and I just thought,
Given the full works.
I understand why this is probably the most celebrated holiday in all of the USA. It's actually a really good idea to be grateful.
It's good to get together with family and just eat a lot. And yeah.
Right.
Yep.
Right. Yeah. So, well, I figured today we would talk about aging and heat. And, engineering's exciting, right? The part where you're laying down the design, where you're figuring out what to do and stuff, that part's exciting. But then there's the not so exciting part, which is the analyzing and living with whether your stuff will work, continue to work, and what its lifetime will be. Now, I did a presentation for VCF back in 2019, and that's what I was going to show today or use as a template. And I was responding to, I had some people approach me telling me I was an idiot because I didn't put heat sinks on CMOS EPROMs, right? And it's like, you don't know what you're talking I'm sorry you don't. I do have a heat sink on the EPROM. It's called the PC board. And, the fact the EPROM lasted 40 years proves it's okay. If it was going to fail due to my stressing it incorrectly, it would have failed 39 years ago. It would have failed 39 and a half years ago. So that's kind of was the impetus behind this was I wanted to treat the people at VCF like fellow engineers. And of course, right now I'm amongst fellow engineers. But my whole thing was, okay, I'm going to talk to you like an engineer. I'm going to tell you what's in my head about why things last, why they break, what kind of compromises I made as an engineer. And, it's a world of compromise. And, it's sad but true. I didn't design the 128 or the +4 series to last more than 3 to 5 years. Why? The people are like, why wouldn't you design it to last forever? It's not my business goal. My business goal is to spend as little money as I can to make a product that works for a reasonable lifetime. And, there's always a budget involved. There's this budget of money. If you work for NASA, you don't have a budget of money, you have a budget of weight, right? Or how much power can it consume? There's always something that's a budget. Who gets to design using no constraints, right?
I remember when I got this computers, I would have only expected them to last a lot longer than, if you had told me that back then, I'd be like, what? 3 to 5 years, this thing's going to be dead. I expect this thing to last like 20 years. But in reality, after you've gone through that phase of life, you're like, yeah, back then people were buying new computers every 2 years or so.
Yeah.
They still are.
Yeah.
And when I say 3 to 5 years, I mean before a component failure, before its first failure. I don't mean the whole thing suddenly bursts into flame. Well, it might. But, you know, it's like that first thing because something like a computer system is the accumulation, the addition, summation of all of those components and all of the problems those components, have and brought to the table. You own them all, right? And they all have to work or the thing breaks. So that's when I say 3 to 5 years, I mean before something rears its ugly head.
And duty cycle plays a big part in that, right, too? Because a lot of people bought a C64 or C128 and used it for 24 hours straight on the weekends, and then maybe didn't touch it all week or used it for an hour here or there. So if you're in a exceedingly cold, icy basement in Salt Lake City, where it's cooling down a lot overnight while it's turned off and then gets warm again the next day, all of these things have an effect, right? But
thermal shock. Yeah. Yes.
Yeah.
Yeah. And I talk and we'll talk about thermal cycling. So now let me be real clear. If you're a collector of old Commodore equipment, heat sink the hell out of it. If that's two different goals. Me designing as a young engineer for 3 to 5 years. If you own a piece of Commodore gear or any old gear, I'm sorry, I keep saying Commodore, and I get asked, well, should I heat sink it? Sure, if you want. It can't hurt. And it may extend the life. Now, it might only extend the life half an hour. And of course, as an engineer, that's not an answer to me. But to somebody that turns it on 3 times a year, that might be useful, right? So,
not to mention, there's very poor thermal conductivity out of the plastic molding of a dip package. But it's better than nothing.
Actually, and we'll talk about this, it has really good thermal conductivity through its lead frame and leads, and to the PC board is your heat sinks. Right. Yep. So when somebody would say, "Oh, you didn't heat sink the EPROMs," yeah, I did. I soldered them into the PC board, or whatnot, or into their even into their sockets. So the one line I had on this site slate, I don't know what to call these. My mind's a blank. But these PowerPoint things here is I misquoted Star Trek, where they said, the court is a crucible in which the truth is distilled out. I read that to mean production is the crucible in which truth is distilled out. If you do low quantity stuff, you may never find the truth, right? You may have a problem and never have an issue. Getting one to work on the bench is...
Yeah, it's so true.
Yeah, right. But make 1 million. All right. If you make 1 million, you'll find every mistake you made will land on your feet, right? At your feet. So,
cutting with a butch wire.
So some unfortunate facts is everything man-made will eventually fail. It just will. Actually, entropy, if you even want to go that far, and we'll talk about entropy a little bit. Entropy is where the whole universe will eventually become one temperature and just be homogeneous, right? Well, long before then, everything we made is gone. It's just turned to dust. Other things is we didn't know, when you design something, you don't know what you'll know in 10 years about how the lifetime of that is. So, it's a reality. People, would say, oh, did you know? No, I didn't know that in 1985 or I didn't know that in 2005 in some cases. So things that affect the product lifetime: materials, how we use the materials, and then the compromise we make. And what always springs to mind, and Ben, you talk about this a lot, is capacitors, for example. How we use capacitors, how we rate them. How are we using them correctly, or can we buy extended time by derating them, double rating the voltage in them and whatnot? So that's what I mean about materials, how we use the materials. Yeah, I'm going to get to some good stuff here, but I'm going to work my way through this.
You can use capacitors as a real cheap, dirty, nasty microphone if you need to.
Yeah, you could. Well, they have capacitive microphones, right? How many different kinds of microphones are there?
That is what an electret is. I could get my audio engineering handbook out and count them for you, but there's probably about 8 or 10 different kinds that are used.
I was going to say at least half a dozen, yeah. Where you use some property of the microphone, we talked about crystals. When they vibrate, the frequency changes. Well, just a crystal can be a microphone.
Yep. The piezo effect. That's one of the most common types, actually, other than basic passive diaphragm. But yeah, not to get off topic.
No, I want to get off topic because this is a boring thing. So I tried in this presentation, I tried to make...
Boring. Well, actually, it's related. It's actually all on topic because I had an experience with heat and aging with one of my microphones. So I have a studio condenser, and it's actually a bloody good one for the price. It was $100, but it's a 1-inch gold spattered diaphragm studio condenser that Guitar Center was selling them in kits on sale. I want to say it was about 2006 that I got this thing, and they're traditionally made. I don't know how they made them so cheap, actually, because they had a fully through-hole printed circuit board on the inside, which meant more expensive, and it had a differential JFET preamp and phantom power circuit.
Right.
So it had a little Colpitts oscillator that was generating a high voltage to bias the microphone. So an electret or a condenser microphone is a capacitor. You have a very, very, very thin film made of, they could be made of mica, or more commonly these days they'd be made of some kind of plastic that's drawn out in a factory, because we can do that more easily and cheaply now. Some kind of polyester with electrodeposited or sputtered plating of metal on either side, and the vibrations in this change the capacitance. So you have to get sound out of that, you have to have it's a very high impedance microphone, so you need a very, very large resistor that pulls it up to a very high voltage to get it biased to where you can get a usable signal out of it, and that signal is very small, so you have to have a very, very high gain, high input impedance preamp. So this is why condenser microphones always use a FET for a preamp,
or a tube. Yeah, because the FET or a vacuum tube for the nicer, higher end ones, you can make a preamp with a super high impedance input and lots of gain. And this one, after some time and some Sydney, I bought it here in the States, and I lived back in Australia for a couple of years. And right around 2010, I was trying to use it for recording some voiceovers for video. And I noticed after it warmed up, it started rumbling all the time. Oh, wow.
And so I had to pull the whole thing apart.
What was the problem?
It was bad capacitors on the high-end preamp. And they had aged, because the thing is phantom powered from a 50 volt supply, and then it steps it up to 160 or something to bias the diaphragm. The diaphragm itself is very robust. They don't they don't tend to go bad. But there was some capacitors in the signal path in the preamp that were just regular MLCCs, and I realized that's where they cut costs, because for audio you normally want to use polyester film capacitors,
right.
Or if you can afford it, mica capacitors, because they're the lowest noise caps. But these I had to replace the ceramic caps on the board because they'd been aging, and when they would get hot, the dielectric it was crazy. But so those mics are working again, and I still use them.
Oh, cool.
But,
cool.
Yeah.
So Bill, you said this is kind of a boring subject, but I find it fascinating because like when I was getting into this as a hobby, it's like, yeah, I don't care. But my company is about to make things that have to be in cars for like a long time, and I'm starting to become interested in this subject, you know.
It's super important for you.
And it's going to be in the passenger compartment where it could be really hot, and
right.
Yeah.
Right.
So if there are things you can do, I want to know what they are.
Right. So I'll throw it out there that environment can accelerate aging, right? Some components are just going to fail, and we'll talk about those. Semiconductors wear out just by virtue that they're semiconductors. Even sitting on a shelf, they can wear out, believe it or not. And that sounds counterintuitive. You think of the moving components as being the only things that would wear out. But the environment, this is how I always start my talk, is the environment can accelerate aging, and these are no-brainers, right? Heat, and we'll talk about what heat does to it here a little bit. Moisture, vibration, ultraviolet light. I would add to that any radiation, right? And ESD, it can accelerate the aging of components.
And this is just regular silicon chips, not like
this is all components.
Capacitors, yeah.
Right. So when you go to, when you go to do a life cycle study on a system you've built, you can accelerate the aging by putting it in accelerated temperature, do temperature cycling, high humidity, and vibrate the dang thing. And it works. You can actually say, okay, we've simulated 10 years of all of those in a 1 year period or whatnot. And we used to have, not an autoclave, but we had an environmental chamber in one of our places and a vibration table. And we didn't do the full aging cycle, but we would sure go in there and look for low-hanging fruit of mistakes we had made.
That's I was listening to Wolke talking about the difference between Tektronix scopes and other cheaper brand scopes.
Yeah.
And that has a lot to do with it. The kind of stuff they put those scopes components through will make them last forever, practically, you know. Not forever, but, you know, a lot longer, and that's what you're paying for when you're getting, or that's part of what you're paying for.
Tektronix, yeah. And Tektronix was old school electronics, I would call them too. So when they designed test equipment to be the biggest, heaviest, we were talking before the show, Mike's got one of those big heavy tables behind him just to hold up all the equipment, and that's the test equipment is built rugged for a reason. Yeah.
It's true. It weighs more than me now.
So here was something that then I went off on, because people said, well, why didn't you design it for 40 years? And so I said, well, you know, there's not even a gasket that would last 40 years, let alone the ones I could afford. A natural, you know, gaskets themselves lasted 3 to 5 years unless I got a silicon gasket, but those top out at 20 years, right? So we won't talk about all the material aspects so I actually went into it because I really like chemistry. And I showed the difference between neoprene and a silicon gasket. When this slideshow actually runs for real life, these spin and they look cool and everything. And we talk about crosslinks in compounds, right? What makes rubber useful are these crosslinks. It's called vulcanization. RTV is room temperature vulcanized. Well, guess what? These crosslinks break, right? Just through age, just through heat, through humidity, through vibration, right? And that's where they stop being a gasket.
Yeah.
One thing I was kind of surprised at when I was digging into some of this older gear that's as old as me is a lot of the wiring, the insulators around the wiring is still holding up even today. Like they picked good plastics or whatever that still are flexible even today, and it's not like crinkling and cracking. Like, they knew what they were doing back then. Yeah.
Oh, here's one that completely surprised me, and I would love to talk to my old mechanical engineers. You know, we have ABS, acrylonitrile butadiene styrene. Yeah, I like chemistry. But they turn yellow, right? Everybody has seen a C128 case that turns yellow. And there was a lot of theories, right? As to, it's too much, it's boron. It's the boron anti-flammable compound added. Well, I thought about that. I'm like, that's the color of boron, right? I'm sorry, I'm saying boron. Oh heck, what was it that they make? Yeah. Now I've forgotten. But the reality is nobody knows that I know of why these cases turn orange, you know, over the type. So yeah, I'm saying boron. We had a chip failure where we had too much boron in the silicon nitride on the PLA of the C64, and it made for bad environmental insulation. And we didn't know it at the time. Again, we didn't know what we'd find out 10 years later. And it turns out, I thought that the chip is coated with a thing called silicon nitride. I thought that it had gaps in it due to the valleys and the hills, and it didn't. It had too much boron in it, was causing the bromide is the chemical I was trying to think of. But it was too much bromide in it. See, I knew by talking about something else I get it. Yeah, so there was bromine. Yeah, bromine in the a bromide compound in the that they used for. So going back to the acrylonitrile, the ABS cases, there was a bromine based compound in there for flammability, and you know the case turns the color of bromine. So I'm like, oh, hey, that could be it. Well, I don't know if that's it or not.
Yeah, this is something that there's
all the halides stack plastics basically. So if you have to put a halide, and bromine's one of the halides, you have to put a halide into the plastic. It's got built-in attack right there.
Right. Yeah. So, and one of the cool things about the Coriolis effect is how Ben and I pronounce things differently, because I call it a halide. Yeah. How do you say aluminum, Ben?
Oh man, aluminium.
No, not even aluminium. Like there's a YU in it somewhere. Aluminium.
Yeah. So you say it like the British do.
Aluminium.
Yeah. So, all right, moving on to metals though. You know, metals oxidize, right? It's just the rate of time that they oxidize. Not all metals. Does gold oxidize? I don't think it does, but the compounds I had availability to, phosphor, bronze, and stuff, they do, but slowly.
The only elements that don't oxidize just on their own are the nobles, from what I recall.
Right.
Because they have a perfectly full outer shell.
Right. But even silver can oxidize.
Yeah.
Platinum doesn't.
The metals that stay shiny usually do so by oxidizing very quickly and forming a passivation.
A barrier. Right.
Yeah.
Right.
That's interesting.
So one of the other... Go ahead.
When you're getting you're choosing Samtec connectors or whatnot, you can typically choose what kind of coatings they have on them. And when I see that stuff, I'm like, what would drive me to choose one over another? And you could get deep into that rat hole of the chemistry.
Well, there's whole books written. I mean, big book. Matter of fact, excuse me for just a second. Let me see if I can grab my book.
That's the biggest part of PCB design and engineering is knowledge of the production process and all the chemical. Like most of the people who are the original gurus of high yield production PCB are people with a material science background, and they've had to spend decades educating electrical engineers on the material science of PCB layout, PCB fabrication, and that's where we get. They're still scratching their heads trying to figure out how things happen, like tin whiskers.
Yeah.
Once we went lead free, and we have tin only or tin silver solders or tin gold solders, the amount of silver or gold in it's less than 0.5%.
Yeah, I can't find my PCB Bible, but I was going to pull out the one by what's his name, Hap. He was at. Yeah. I've got the.
It always makes me feel uneasy. Like I picked one between the three choices you have of what type of coating to put on the leads, and I'm like, whoa, did I have any justification for picking that one? No. Even they're all roughly the same price too, so it's I guess you have to read up on it. Yeah.
It's probably depends on duty cycle, the compatibility of what's connecting into it, like the cable, the mating connector probably matters. What it has.
Oh, okay.
And how long is it going to be in storage before you use it is probably a big factor too.
How many insertion cycles? Is it inserted once or 100 times or 1,000 in its life? Those can matter. What I've seen is companies will tend to find a policy for what kind of coatings they want. They don't want every engineer just using whatever coating based on their knowledge. They come together and we say, okay, we're going to use phosphor bronze or something for our standard connectors, unless it's the analog connectors, then we might use something else. But we generally would, I was told which ones to use because somebody else researched it for me, basically, and put the work in. Yeah. So there's another form of metal reaction, which is a galvanic reaction. And that is two dissimilar metals will create a current between them, and it basically causes one of them to rust, to oxidize. And if you actually open, I don't know if I have one, an old PC board, you'll see like the steel screws where they touch the tin something, it's rusted. Yeah. It's like, why are those components rusted? Well, it's made itself into a tiny little battery due to the dissimilar metals. That's how you make a battery, is have two metals with two different activation energies, and you get current flow. So now, what we used to do to prevent oxidation in storage, Ben mentioned storage, we used to throw mothballs in with our chips. For nowadays, I don't know, can we even get mothballs? Did they have mothballs in Australia?
Yeah, I think my mum still uses them to, and because every time I visit and give her a hug, she's wearing some.
She smells like that.
Hand-knitted sweater, and she smells like mothballs.
Yeah, it's a horrible smell.
Right.
It reminds me of my grandmother too. Yeah.
I think we don't get them here in America probably more than anything because people just don't want to use them because of the smell.
Yeah.
Well, they're becoming, it's a VOC. It's a dual benzene ring, which is a funny way of saying it's from a family of chemicals that cause cancer, right? A carcinogen.
Is it extracted from crude oil like gasoline?
I would believe so. I believe it's cracked out. Yeah. I know places like England, it's just outlawed. You can't get, and probably a lot of Europe, you can't get mothballs. So what's that leave? Nitrogen, argon,
It's still used in Zippo lighter fluid, I think, because it has that same smell.
So you use mothballs for electronics, you're saying, not just moths in clothing, right?
Right.
You would store electronics with mothballs.
We had a batch of surface mount chips one time that didn't solder right, and we traced it to they were stored wrong, and the running joke was nobody threw any mothballs in with it while it was stored. Well, nowadays we also know to store them in, where I store my chips, I have one of those big seal tight containers, and I have a whole handful of the anti-moisture stuff in there. Yeah. So now, when we design, some things have limited life, just right off the bat, batteries being one of them, right?
Yeah.
Show me a battery that lasts 20 years, let alone 40. I had the pleasure of, at a Hackaday event, there was somebody there from JPL, and they asked him about the Mars rover battery. And somebody said, did you use a super cap for the battery. And me and the guy both kind of chuckled, right? It's simultaneously. Supercaps didn't really exist back when they made the Mars rover, not when it was being designed. Back then, the only battery that we had any real lifetime stuff on was NiCad. So nowadays, we got a lot of battery chemistries. And I've even been asking around, does anybody know a good Bible for batteries? Oh, you know what? I just realized I haven't been watching the chat room here. Hang on a second.
Oh.
I think, I think some of the batteries wholesale sites actually have some pretty good documentation on them. I was going through learning more about the different lithium technologies from Battery Junction, because I was buying some lithium cells from Battery Junction for things like this. The sign behind me is running off a custom-made lithium battery. And so there's some really good articles on some of those sites that go through the different things. I hate nickel cadmium batteries. Always hate.
Yeah, I didn't say we liked them, but that was our battery that back in the 80s, 90s, you know, that we had any real reliability data from that I know of. You know, trust me, I'm just a lowly engineer who, you know, had a small career. But that was the only battery we had back in the day that could do. And NiCad had things like, you know, memory to them. If you didn't discharge them all the way, you couldn't then discharge them all the way later in their life. All kinds of things.
Oh, wow.
So limited lifetime component. And then, of course, my favorite trick, if I show this, you can see the corrosion, the leaking of the batteries, right? Mm-hmm. They get all over the board, as you see here. And then Dallas made a wonderful component that was, back in the day, before flash memory was prevalent, cheap, easy, we had to do battery-backed CMOS. So we would actually solder batteries to the board. Well, guess what? They go through the drag solder machine and short out the battery leads. So it's like, so we had to lay them out so they wouldn't short out the leads, things like that. And they came out with... Go ahead.
Battery-backed CMOS had even been used for motherboard BIOS settings all the way up until UEFI motherboards started coming out.
Yeah.
And speaking
there was a coin cell in there.
I still have Core i7 motherboard that has a button labeled on the motherboard, labeled CMOS reset. And
right.
a button cell battery.
And it would either short out the battery or open up the battery, one of the two. You know, that was the reset, was to pull the battery power from the board.
I think
I have a story about those Dallas chips. They have the battery built in, so they were.
And that's what I'm showing here. Yeah.
Some of the older equipment, like this old HP spectrum analyzer, has a battery in it that has the calibration constants in it, but it's only spec to last like 8 years or something like that, and the thing is way beyond that. So it's like, things they didn't design them to last forever.
And this is one of those smart sockets. So Ben, you were saying you had a story about one?
I had, I actually flipped a 487 laptop back in the days when laptops still had a monochrome HSTN or whatever they're called, LCD, and they were really, really expensive. I managed to come across one that a government auction site basically let me take it home for free because it had the CMOS password set and no one had the password. So I thought, I'll tinker with it and see if I can hack it. Yeah. And it was a 486 laptop. I took it sometime later to another place I was working at the time. I was doing servicing on electronics gear. I had all the desoldering workstation and everything. And it had one of those Dallas chips on the motherboard. So I thought, I'll try this. I desoldered it out of the motherboard very carefully. I shoved it for a few seconds in a piece of aluminium foil and soldered it back in. And sure enough, the password, because I basically shorted out that battery, but just long enough to clear the CMOS, but not enough to completely deplete the battery. So I soldered it back in, everything worked, and I sold the laptop on. We didn't have eBay back then. It was just the local trading post or whatever. Someone came and bought it for their college student. So,
Right.
yeah.
Now, I one of the schools I used to be the ISP for, their routers started dying. And sure enough, I looked at the routers, and built into them were these Dallas parts. These are Cisco routers, high quality stuff. And if you think about it, that means they were designed to fail in 5 years in their routers. They're not consumer goods. And I understand why they did it. It was so tempting to use these built-in battery stuff because it was so easy compared to building it yourself, but you would still have to replace the battery.
Yeah. Well, and these parts, they just weren't that cheap. But
No.
I guess they wanted to save board space too.
Yeah, it does that. And importantly, not everybody was good at the logic that write protects the static RAM. That's actually how I became an engineer. If I tell the first story of my engineering career, I was a production technician, and I found a way where I could ruin the contents of the battery backed up constants for digital weighing instrumentation. And we weren't doing the logic correctly to put the CMOS RAM into a safe mode. And I wrote a paper up on it, and eventually that, was put up or shut up. They took me out of production and made me an associate engineer. And I redesigned the way we used our CMOS batteries at a company called Pennsylvania Scale Company. Well, so I knew things about it, but I had learned the hard way. We as a company had learned the hard way what would fail out in the field. And it dealt with the way brownouts and everything else would happen. So yeah, I kind of owed my career to the fact that we screwed up making battery backed up, battery backed up CMOS RAM back then. So now the other story that goes along with that is then when I got to Commodore, and I get put in charge of this TED project, this thing, right? I look at it and I say that reset circuit's not going to work. I will be able to, using a variac, AC variable voltage, I'll be able to screw up that reset circuit. And I knew this from working at this Pennsylvania Scale Company, where I could always find a sweet spot for screwing up the circuit. So yeah, the Dallas parts were easy to use too. They were reliable to use. So, hey Ben, somebody reported you're hard to hear. I don't know if there's such a thing as getting closer to the mic or if it's just your bandwidth.
It's probably my bandwidth.
Okay.
But I'll switch to my earbuds if it helps.
Now, you don't have an echo. It's not an echo from what I understand. So, all right. So here's a limited lifetime component because they, wait for it, they dry out. They dry out with heat. And the problem is, even this is not an airtight seal right around these leads, right? So heat really will drive the electrolytic out through the gap around these leads. They used to actually have vent holes in capacitors, electrolytics, so that they wouldn't explode. Well, guess what? They just dried out quicker, or we actually were drying them out when we were cleaning the PC boards. So, we would put them through basically a chemical bath, and there's a vent hole, and we're just contaminating the caps. So we had to use sealed caps, but they're only partially sealed. And
you can only get 30 years out of one of these things at most, 40 years, and they'll be done, right? But
I'm surprised any of them work that are 40 years old. But my C128 still works, and so yeah. Now, people.
Yeah, that's a classic audio amp conservation task. People are constantly getting their old guitar tube amps because they're also getting really hot all the time. So the caps dry out even faster. So you take them in and you get a cap job, they call it. So basically just replace all the caps.
Recap.
Yeah.
Right. Now, there's a school of thought that says if you just spent a lot of good money and bought some old piece of work like this, before you even turn it on, you might recap it. Now, I don't necessarily do this because I'm not a collector, but a true collector, before they'll turn on some equipment, they'll change the caps out because having bad caps in there can damage the equipment. So it's better to change them out ahead of time. Now, I'm from the school of thought that says if you recap them badly, you create more problems than you fixed. You know, so you have to do it well.
Yeah.
Also, time is money. It could take a long time.
It could.
You could buy a new thing off of eBay in the amount of time it take you.
But the thing you buy off eBay is just as old as the one you're trying to fix. You know, eventually we're going to have to fix the things.
I guess, money doesn't matter if you're a collector. You're like babying these things and like,
Well, that's why I say, you know, go ahead, put a heat sink on. You know, if you're a collector, you've invested in it. Yeah. Whereas an engineer, I'm trying to design something that lasts long, you know, that hits the center of the road. So, hey, Wes just said, hey, guys.
Why wouldn't you use tantalums instead?
Somebody just posted that. Yeah, and so I'll tell my story where whenever I would turn on a new circuit, a circuit that hadn't been turned on before, if it had tantalums, I'd put a piece of paper on top because the tantalums have an infant mortality mechanism of exploding. And we used to say a hot piece of tantalum in your eye will really ruin your day.
Oh, man.
So, yeah. Because, you know, I didn't wear goggles while working on electronics. So
besides which, tantalums are really way more expensive than their equivalent electrolytic. They can be more reliable if you get ones that are aged in well, made by a reputable manufacturer, but then you're paying a ton of money for them.
Right.
Is there a simple explanation for what's going on with tantalums? Is it just something that they are or is it a chemical thing that occurs and they just blow up? Or
I assumed it was a chemical thing. Yeah, that it was partial the way they're made and they're volatile. So that a short in them is not just a short, it's an explode. It's sometimes you get a short and it just zaps the short away, right?
Okay, yeah.
Well, other times it explodes.
It's how they're made too, because the very nature of a tantalum cap, it's like you imagine that the tantalum metal is like a really fine sponge inside. And that sponge, the reason they're very compact, they have very high capacitance for the size, is because it's a sponge. It's kind of like what's that world's least dense solid is made of a similar kind of material. It's like a plastic that's almost see-through.
Right.
But the tantalum, they make this sponge out of the tantalum, and then they apply a voltage in a solution that creates an oxide layer around all of that, and that gives you the insulation barrier. But that's very, very thin, and when tantalums age and die, if they're not going to, they last a very long time. But when you get one that's not perfect, when they fail, they tend to fail with a short circuit, and that's what makes them go up spectacularly. Whereas electrolytics, when they get old and dry out, they just fail open, like their capacitance drops until it's almost nothing. Right.
Or if you have a pinhole in your dielectric, it's not some will heal, right? Some capacitors.
Film capacitors are usually self-healing. Yeah, they have special polymers that'll go in and fill the space over time. It's pretty amazing technology. They cost a lot.
So I learned that lesson. If you have one of your rails shorted to ground, go look for a tantalum cap that failed, and that's probably doing it.
Yeah. And now somebody posted in the chat that tantalums can even explode in storage. I hadn't heard that. I didn't. Man. I thought you needed the potential of lots of voltage, or not lots of voltage, but you needed the energy somewhere. I didn't think it was the actual tantalum exploding, but I could be wrong. So here I've shown the electrolytic capacitor lifetime. I got this from Illinois Capacitor. And there actually is a formula. So that's the only thing I'll show here is there is a formula for how long your caps will last, you know. So as engineers, we actually kind of do know how long this stuff, and again, it's about compromise. I'm not putting a 100-year cap in a consumer good, or, you know, I probably can't afford one, nor could I afford the size of it and everything else.
Or even in a missile.
Yeah, right. The missile's got a limited lifetime, right? It's a huge storage time, but limited lifetime.
Yeah. I've met engineers who are tying themselves in knots over making Oh, it's an aerospace application. It has to be like absolutely
reliable,
best quality of everything. And it's like, and then realizing, wait a second, it only has to last 20 seconds before it hits the target.
Yeah.
But it's got to be a robust 20 seconds.
Oh, it has to work. It has to work. That's absolutely non-negotiable. But
right.
Yeah.
So failures, a typical failure cycle. I showed this because again, when we would make a million or something, early failures, the project wasn't done till you've been through part of your production cycle, because you get infant mortality, and I'll show the bathtub curve here in a second. Actually, it's right here. But
everyone knows that.
There's failures. Yeah, but there's failures due to engineering issues where I didn't do my job right. So, and then there's other failure, and so we remediate it. We go in and say, why are we failing in production? Let's change this cap for a better cap, right? We also have fabrication problems where the auto insertion machine in the old days, was set for the wrong pressure, or it was crimping a lead over or something. So we would have to deal with the manufacturing process as well before we could get into the extended, random failures of just aging. So I was just, I did this just to show that we actually would go in there and respond to early failures as if our lives depended on it in mass production. A 1% to 5% fallout of a million is a lot of skids of bad product. All right, here's everybody's favorite bathtub curve. And, it almost goes without explaining. We're all engineers here, right, on this call. Early failures, and then we just get into the long lifetime of the product, and then it starts to wear out. And Mike and I were talking off screen about 2 sigma and 3 sigma, and when this starts to kick in and whatnot. Be aware this exists. And this is the size of the thing that we're talking about when I say 3 to 5 years. I'm talking about this little knee here. Let's say I designed some for 5 years. Right here is where the 5 years part is, to me, where it first starts to be noticeable. So they say 1 sigma is where it rises above the noise level. I always took 2 sigma. Ben, have you ever worked with sigma and reliability? And
no,
can you?
Not beyond my. Not beyond my engineering practice classes at university.
Okay. So here's the thing. Do chips wear out?
Of course not.
Right?
Yeah.
There's no moving parts.
Migration.
There's nothing to dry out. And again, I did this in response. Somebody was telling me that the proof, that the parts were failing after 40 years, that we must have misused them or they wouldn't fail at all. No, chips age, right? And we'll talk about that here.
This electromigration is one of the primary causes, right?
Yep. Time-dependent dielectric breakdown. The dielectrics they just poop out, right? And there's dielectrics in chips. There's hot carrier-induced characteristics. That's where there's actual a time-dependent can break down just due to time passing. Hot carrier-induced characteristics are where you're actually using it over time. And then there's electromigration, and I'll talk about those here. Yeah, we're running out of time. I'm not going to talk about the math of reliability. I will say that this here deals with something called Boltzmann's constant, where the failure rate is related to the temperature, the junction temperature. There are some rules of thumb, but I've seen some people go off the deep end with the rules of thumb, like, oh, for 10 degrees C, you double the product life. Well, yeah, if you were only dealing with Boltzmann's constant, yeah, maybe so. But a computer system's a complex thing, and so there's a lot of failure mechanisms going on. All right, here's one. Chips can wear out just by having voltage applied to them. You wouldn't think that. You'd think it'd be current, right? But just having voltage applied to chips causes them to fail, and there's actually a formula for that. Here we go. Time-dependent dielectric breakdown. Let me make this bigger.
This is the good stuff. What does this mean?
I wish I remembered. It's
Maybe we could talk about electromigration then, because that's the more common one.
right.
Yeah.
So what it says here, in other words, the dielectric area is a tiny spot to increase conductivity compared to the rest of the dielectric area.
Okay.
Breakdown occurs after a certain amount of time due to the oxide is subjected to electrical stress during product operation. So basically your dielectric wears out. So that's one failure mechanism, even though it's not a moving part. Hot carrier injection, we were talking about that. Electrons just end up in the wrong place. Is the way to think of that. Here's an FET from the side where you've got your zone beneath it. Well, not all the electrons go where you want them. Some will get into your dielectric here, into your insulator, and contaminate it. So that's what we're showing here. Let me make that a little bit bigger for a second.
Messes up the doping, I guess. Interesting.
Yeah, it messes up the dielectric.
It could cause the gate to start to become
leaky
lower resistance. Yeah.
Yeah. Here's one for you. Now, let me make this.
Okay, what's this?
That's electron migration on a trace in a chip.
Really?
It actually scooped out the metal and deposited it further down the trace.
Yeah. Oh, wow. So it physically
That's cool. I love that
metal?
picture. So there are moving parts. The trick question is there are moving parts in a chip,
There are. They're called electrons, and they're
called electrons.
Hit and move. They can hit and move other stuff.
Yeah.
That's the crazy thing, right?
So thermal stress migration is where metal atoms migrate in the presence of thermal stress alone, with no electric current applied. So here's another way your chip can break, with over time and just with temperature.
And the previous one, the electron migration, you can't there's nothing you can do to say like, oh, I want to run my system cooler with heat sinks and whatnot. Electromigration is just going to happen anyway.
Yeah,
you need a fatter trace.
A fatter trace would help.
You need lower current for the given. Yeah.
For the given square area. Yeah.
Just trying to make everything smaller, and that's what causes it. No one really knew what this was until they started getting down below like 130 nanometer processors. I don't recall ever hearing about electromigration until 65 was around common.
So now, one thing I won't talk long about soft errors. This is basically where you lose a bit in your a bit in your RAM cell or EEPROM cell, and it's a soft error. In other words, it's recoverable, but you lost the information that was there, and this is caused by electron hole pairs and the physics that go along with them. So yet another failure mechanism. Let me try and remember here. Yeah, this is same thing when I'm showing an EEPROM where there's a floating gate. Again, it's all about this insulation right here that makes it a floating gate.
So in all of
here
these,
you go.
The reason why you look at the data sheet for any of those old EEPROMs or SRAMs, they have, EEPROMs in particular, they have a guaranteed data retention time, but it's only if you program it once.
I wasn't aware of the once part of that equation. I just picture EEPROMs from the moment you charge them, the charge is trickling off that floating gate. Now, that may or may not be true, but that's the way I mentally picture it. So here we go, silver ion migration. This is, Ben, you were talking about this earlier in the show.
It's the whisker thing?
Yeah, it's the whisker thing.
Oh, okay. So this happens with silver as well, not just tin. I guess it could happen with pretty much any metal.
Yep. Yeah, because movement is heat. Oh, here's one. You'd think that the chips are waterproof. They're not. That resin is not waterproof. It is water resistant, like your old Timex watch, but it is not waterproof. So
And
it
this is
does
why
get
we
in
have
through
to
the
bake
lead grain.
chips if they've been, yeah.
So this is why heat, vibration, and moisture can break a chip. You think, well, how's that happen to a chip? Well, a chip's still a physical device, and that action can induce the moisture to flow through the resin. So somebody's saying
So
silicon's a
how
very
do we-
viscous liquid.
So
Yeah,
Bill,
go
how
ahead.
do we mitigate these? How is
What do you
Mike
do?
going to avoid these problems? Because
Or-
he's about to go to production with an automotive, no less,
Well,
product,
I guess
right?
part of it is like you probably make a bunch and measure it to see if you have a problem, or
There's some of
you
these
could
things
like do some
they
rules of
take
thumb to
so
avoid
long.
it.
Yeah,
I was
you
gonna
buy
say,
better
some of these things
components.
take so long.
Yeah.
Some of these things take so long to reveal themselves. How do you test for it?
Yeah.
So you test for it by accelerating your heat, temperature, and vibration, and you really can do 10 years of you know what? I'll post a couple of reliability data books to the Discord channel. By the way, we have a Discord channel. Go to Coriolis-effect.com. You'll find a Discord invite. I'll post the links to a couple of reliability handbooks, but you really can predict the future by accelerating aging, and you really can accelerate aging with humidity, heat, vibration in a test chamber. So you
And
really
you
can
got-
get
and
10
you
years
use
of...
that- You use that for the 128, I assume, like MOS and Commodore had the lab to do all of that, or you?
No,
had
we
the-
make
winging it.
consumer toys. Yeah, we just bought off-the-shelf stuff in mass quantities and threw it together. Now, when I worked at an instrumentation company, we had the whole the environmental chamber. We had the vibration tables. We had those, and honestly, we were looking for problems we created, not so much the components. We were relying on the manufacturer's data about their components. So to answer your question, how do you mitigate this? Well, you find a manufacturer that's dealt with the problem and fixed it, or fixed it to the degree you need it to be fixed.
Yeah.
And that's money.
It kind of reminds me of
And size and weight. You know, if you work for NASA, those things are important too.
Here comes a musical joke. It reminds me of, I used to work with a lot of musicians at Altium, and we would go out to lunch and invent heavy metal band names if we were to get in a band together. Well, one of the names that came to the table was Shock and Vibe.
Oh, there you go. There you go. So did you ever make a
No.
band name? No.
No, people were too busy working all through the night.
So why not store chips in the freezer then? Why not put your whole computer in the freezer if we've said that temperature... Oh, so let me back up one, because here's the thing. We've said heat causes aging. So people think, okay, don't turn it on. Put heat sinks on, whatever. Guess what? Room temperature is still temperature, right? It's less temperature, but it's still temperature.
In terms
So
of Kelvin,
when we say... When we say in terms of Kelvin, right?
Yeah.
So when we say heat breaks stuff, it breaks it faster, but it's still being broken at room temperature. So just storing your stuff, it's getting older. It's wearing out just with room temperature heat. So the question starts to become, well, how do we keep our old computers working, right? So one answer might be, well, can we stick it in the freezer? Why not stick the thing in the freezer? You know, put it in a waterproof bag or something. Well, that turns out that's bad too. There's something called aluminum sliding. The resin, it basically things contract and expand at different rates. And when that happens, it can actually peel up here, let me make this bigger.
Puts it under a different kind of stress.
Yeah. So it turns out sticking them in the freezer is bad too. So it pulls the wiring towards the center of the chip.
But I'm going to have units in a car that are out in the cold.
Oh, automotive's horrible. Automotive is hell on earth.
Oh, man.
It's the worst. It's actually IPC classifies automotive applications as the most harsh environment
Of all, worst
Yeah.
in aerospace.
Yeah. So here's another reason cold is too much cold is bad. Depending on the quality of the resin, you know, the resin is the black body of a chip, right?
Okay.
And the resin isn't pure. It's got big chunks in it, relatively speaking. The more you pay for your resin, the better the resin, but consumer resins have these bigger chunks, and temperature can cause, again, differential movement, and here's a piece pointed down. Picture this getting bigger. You could see this point right here is about to jab down into this part here. Mm-hmm. So the resin, the quality of the resin can affect your temperature qualities. And again, this is one of the things you fix with your by buying the components from manufacturers have already done this work. All right, thermal cycling. When does a light bulb blow out usually? Does it blow out while it's sitting still?
When you first turn it on.
Yeah.
When you first turn it on.
Yeah.
So I came up with this idea of using a thermistor-based, a phlogistor-based, what do we call the phlogistor's? What's the other word for them?
A Peltier element?
Peltier devices.
Okay.
To actually cool it when it's running, but to slowly warm it before you turn it on. So it's kind of like, picture you really wanted to save your components. I think we should have heat sinks that pre-warm the chips. And that sounds counterintuitive, right? But slowly warms them to the operating temperature. And then when you add current, there is no thermal shock. So I wanted to make heat sinks that slowly warm the components up. People just thought I was nuts, right?
It's like starting a diesel engine, and you've got to wait for
It
the
is.
glow pods first.
Yeah, yeah.
But
So I think
you
I'm
know
running
what?
out of slides
I know.
here.
Have you guys ever seen this? I've actually blown more than once in my life, an incandescent light bulb, and it's still lit up because
It shorted in a funny way.
no, because the current was able to jump from one end of the filament to the other through a vacuum. If it was already warm, if the whole thing was already warm, and
So it ionized.
and I would flip it off and on again, and the filament broke, but it was literally arcing. You can't see the arc. There's almost no gas in there. But the filament was still lit up, and one side of it was wobbling like crazy.
Yeah.
Wow.
Of course, after you turn it off, then it won't start up again. I've seen that. Maybe that happens more in high voltage countries, but that I've never seen it in the States. But in Australia, everything's 240. So.
Right. Yeah, I broke a light bulb once that was turned on. I accidentally hit it with something and broke the glass. So I got to see the lifetime of a tungsten filament when exposed to open air. It was like several seconds. So yeah, the way I ended this presentation as I got near the end was, so how the heck is this 40-year-old computer's designed last 5 years working anyways? And the answer is statistics, but I'm truly amazed any of it works. I truly amazed. Let alone people bitching at me that the TED chips break after 30 years or something. It's they're meant to break. We only spend a certain amount of money.
Even if you're not like making a product, you might be buying old test gear off of eBay, and you might be interested in like the failure modes and how to repair them and how long you have left. And
So
really important.
People ask about heat sinks. Now, there's three ways heat's transferred: conduction, radiation, and convection. A heat sink uses convection, right? It heats the air around it, and it radiates to the air around it too. But those aren't the best ways to transfer heat. The best way to transfer heat's conduction, and that's why I say the PCB is the primary heat sink on a device, whether you know it or not. And finally, we were talking about this off screen. The closed box problem is if you have a closed computer and you put heat sinks on it, on your chips, and you heat the air in the computer, unless you remove the heat from the closed box, you still have the same problem. You've heated the air.
Delayed it.
You delayed the transfer.
Like baking it all inside there.
Right. So the trick is, how do you conduct it out of the enclosure? And that's why, let's see, do I still have it here? I have one of those big metal shields here somewhere. In addition to being an RF shield, it conducted the heat completely out of the area I was interested in. So it was actually a pretty reasonable heat sink for all involved. And today, you know what, Ben, at some point we'll do a show on how to calculate thermal resistance and whatnot.
Oh, yeah, we need to do that. That's a good topic to do. Yeah.
So let's see. Somebody mentioned I never had a C64 breakdown to wear. Well, cool. I have. We had C64s break down just sitting there after 1 week old. So I'm just reviewing the comments in the thing here. So I'm out of things to talk about. But again, this was a presentation I did for VCF, which was sponsored by Hackaday. I love the Hackaday angle, so I'll go ahead and end on that slide. And so that was aging in heat in a very fast nutshell.
It's fascinating.
So any comments, Ben?
My head is full.
Okay. Mike, anything to add?
Yeah, it kind of makes me wonder, like, what are things that you can do? And it sounds like thermal management is probably a big important one. And you mentioned, Ben, thicker traces, but that might apply to really thin things inside of silicon chips that you can't.
Or really high current. Yeah,
really
it's not a normal thing. Yeah.
Electromigration doesn't really. I'm sure it happens on printed circuit boards too, but it's no one reports it.
Yeah. Right.
CAF is a much bigger problem. You know, cathode. No, was it something anodic filament? I forget what the C stands for. Where some of the copper seeps into gaps following along the fiber weaves in the because there's not perfect wetting between the resin and the fiberglass in some locations. And then copper can gradually creep along there over time and short out against other nets. So that's, but these are all pretty well understood. Yeah. A lot of these things you just don't have a problem if you use a good reputable fab. So, yeah.
Hey, this one's to Johan Grip. He just posted in the in the chat channel. Johan, John, didn't you say that you had 2 traces fail on a 128 just due to being old? John just posted that solder mask leaks. Yes, absolutely. It's not meant to be watertight. But for some reason I was thinking he said that he had 2 traces that had corroded off the board or something. And so he had to go in and replace 2 traces and which I never want to troubleshoot a 128 to that level again, ever. I mean, I used to do that on a daily basis, and I had equipment to do it. So all right. I'm out of things to say. As Ben said, my brain is full. Mine's now empty. I just puked it up all over the PowerPoint stage here.
Cool. No, but let's do that though. Let's plan out a few future episodes. We'll definitely do one on thermal management. That's a good one. It applies to everything, really. And Mike, thanks for joining us.
Thanks for having me. Yeah,
it's
always exciting. Yeah.
Your instrument collection keeps growing.
It's a way of making it look like I know what I'm talking about when I don't.
It makes a good backdrop.
Dude, I'll tell you what, there's one piece of gear I've wanted for a long time, but I haven't been able to separate myself from the money for it, but it's audio analyzer. HP 8, I think the 8931B or one along those lines. They usually require renovation these days, though, because they have extremely sensitive, extremely low noise FET.
Yeah. Does it do like harmonic distortion analysis?
Yeah, that's why I was going to ask. Yeah.
They do DHD, IMD.
Oh man.
Intermodulation distortion.
And a few others, and they're just beautiful, but they're old. So they cost probably $1,000 to get one, which is not too bad. Yeah. Then you have to renovate it with new FETs, and the FETs are getting harder and harder to find.
Right.
So
what would you do with one?
Audio analysis.
Play.
I test preamps, preamp designs, audio power amplifier designs.
Oh,
for
okay.
THD.
Yeah. So if you're actually
THD,
doing work, yeah.
And intermodulation distortion, and indirectly testing A to D and D to A things with, you know, other parameters of the analog to digital domain conversions. But
so one last thing, somebody in the chat room asked, Chuck Peddle was on a live stream with Jerry Ellsworth and myself, and he mentioned that the early Intel's 4004s, 8008s were calculator chips. I kind of think of the 4004 that way, but I'm not going to say they were strictly calculator chips because they've got more features and functions in them. But Chuck Peddle was there. I wasn't. So I'm going to pass on that question. So he's my version of a semiconductor god. And I'm sorry he's no longer with us. So, all right. Well, thank you, everybody, for joining. It's 13 minutes past the hour, so we had a good run at it. Mike, so thanks for stepping in. It worked out this way as well. Ben, good seeing you again. And we'll see everybody next week.
okay, have a great weekend.